Hi everybody, I'm Greg Kiar, and as you may remember, I gave the Brain Hack 101 lecture in week 1, and today I'll be talking to you about exploratory data analysis. We'll start by going over 6 different types of analysis in data science, and then we'll dig in and do some descriptive and exploratory analysis on the IRIS dataset, which is a popular dataset for benchmarking in data science. And then I'll leave the floor open for you to finish that analysis and point you to some resources for doing it again on neuroimaging data. All of the notebooks and code and everything like that I'll be going through today can be found on GitHub at github.com/brainhack101/exploratory data analysis. And there should be a link accompanying this video as well that gives you that URL. So let's dig in. As I mentioned, there are 6 core types of data analysis. You have descriptive, exploratory, inferential, predictive, causal, and mechanistic. And as you go down the list, they become increasingly complex and reliant on the previous methods or previous analysis. So descriptive analysis is the highest level and the most simple, and we all do it without even really thinking about it. It is, what does my data look like, in that how is it structured? What type of files are they? How many observations do I have? How many classes are there? What are the features that I'm observing? Do I have any values that are incomplete? Are any partially complete? Are there values like infinity or negative infinity or nans? Things like that. It's just doing kind of an audit before you actually start visualizing your data. So this is the foundational step that, again, I think we all do automatically. Now, exploratory analysis is something that a lot of us do without realizing it, but we should all probably be doing more of and be doing a more mindful job of it. An exploratory analysis is looking at your data and trying to understand the underlying properties of your data prior to digging into, say, doing an inferential or predictive analysis. So let's say you're interested in age, and you're interested in the size of the brain. What you might try doing is plotting different statistics about the size of the brain and, say, coloring all your data points by the age of the subjects, and trying to understand what trends exist so that when you're going to do your inferential and predictive analyses, you'll be able to go in with a reasonable hypothesis. So inferential analyses, as I said, is essentially hypothesis testing. Is there a difference between 2 subpopulations of my data? So is there a difference between older and younger people based on brain size, for instance? So you can do these tests, and if you do observe a difference, you accept your alternate, and then with that you can move on and do predictive analyses. So if given a new set of brains, are you able to predict what age they are? What age the subject is. So again, this is a more complex analysis that requires success in the previous ones. And now causal and mechanistic analyses are again increasingly complex, and they're less relevant for MRI or EEG, just because they're much too difficult to answer with in a lot of cases. So of course I'll just explain them as their names suggest. Causal is trying to understand, okay, if we have this relationship, which direction does causality flow? What is the cause of this relationship? And mechanistic is the underlying mechanism that is responsible for producing that cause. So again, these are just our analysis levels, and for the most part, what you will always be doing, no matter what your data is you'll be doing descriptive and exploratory analysis, and sometimes just stopping there. So that's the general part, and that's what we're going to focus on today. So the first thing we're going to do, of course, is import our packages. You'll notice I'm using pretty standard libraries, NumPy, SciPy. We're going to use Plotly for visualization. One thing I really like about Plotly is that you can interact with the plots after you visualize them without having to change any code. So that makes it really useful for getting more complicated figures than you want to spend effort making. And then also we're going to use scikit-learn just to get the data set and some other SciPy functions. So we're going to load the data set, and first things first, let's do some descriptive analysis. Let's just print the data set. What is that? So we notice right away it's a dictionary. There's a couple keys here. The first one is data, and then there's a big matrix of data. Looks like it's 4 by a large number. And target, same thing. It's 1 by a large number. Target names, description, and okay, wow, this is difficult to read. So already we have learned some things. We've learned that this is stored as a dictionary, which means that we can simplify our life a little bit. So okay, great. We see that there's 5 keys here: description, data, target, target names, feature name. Perfect. So let's look at the description. So as we mentioned, there are 4 features, 150 observations, and there's 50 in each of 3 classes. So in other words, there's 3 types of flowers. There are 4 features that we're observing of each flower, and there's 50 observations of each of these types of flowers. So then there's some more statistics. There's no missing values. This is giving attribution to the author and citation information. Great. So now let's just confirm that that's what we expect it to be. So again, here we're just going into the iris data set. For each of data, target, target name, and feature name, we are getting the shape or the length. The different function is simply based on the type. So if it's an array, we'll do it this way, and if it's a list, we'll do it this way. And strip out wrapping and all that kind of stuff. And what we end up getting is the dimensions of all these elements. So the data, as we said, as we observed, was 150 by 4. Target 150 by 1. Target names 3, and feature names 4. Perfect. So we have 4 features, 3 classes, and 150 observations. So that's exactly what the description told us, and it's nice to confirm that. So now we can jump into doing some exploratory analysis. And again, this is by no means meant to be an exhaustive set of analyses. It is simply meant to be a springboard so that you can try further analysis and kind of have the building blocks to do this yourself. So we'll start by looking at, let's say, the first 2 features, and we're going to color the points by class and see if any trends emerge. Okay, so the first 2 features happen to be sepal width and sepal length, and the 3 classes are setosa, versicolor, and virginica. So we notice right away that setosa is quite a bit different from the other 2 based on these 2 features. Neither one independently, but together we're able to draw this nice diagonal line that separates these classes. One other thing, by the way, that's nice about Plotly is that you can toggle subgroups of your data, so that you're essentially able to look at subgroups of your total cohort, and instead of having to produce multiple plots to get this effect, you can just produce complex plots and simplify them, which I think is a nice feature. You can also pan and zoom and things like that, and you just have to double click to get back, as the tooltip showed us in the corner. So great. Now this is quite informative, I think, but let's do it for all pairs of data. So that was just 1 pair of features, and now we'll do it with 4 features, so we're making a 4x4 grid. Again, this is pretty much the same code with a little bit of formatting magic added, nothing too fancy. So, so what we see here is that on the diagonals we have just a 1-dimensional line. Essentially, it just happens to be slanted because I didn't bother telling them to make it flat. And the name of that feature is underneath each column. And then on the off-diagonal blocks, at the intersection of a row and a column is the plotting of those 2 features together. So for instance, right here we have in the 3rd column, 2nd row, we have petal length versus sepal length. So again, we can start to see that there's some separation, and always it seems setosa is more different from versicolor and virginica than they are from each other. But in some of these features, they seem quite different from each other as well. So for instance, if we look at that example plot, the 3rd column, 2nd row, we do see that there is somewhat of a separation between green and orange here. And similarly, if we go down just to petal length, there's somewhat of a separation, and it's not as clean as setosa is, but there is less overlap than, say, sepal width versus sepal length. And also, another interesting thing is that it's good that we didn't try, after doing a first exploration, we didn't stop there and use sepal length and sepal width as a classifier for separating out setosa, because looking at petal length, for instance, we see that we don't even need to do a 2-dimensional classification here. We can simply put a line in the sand between these 2 classes, because notice the maximum petal length for setosa is 1.9 and the minimum for versicolor is 3. we can put a limit at, say, 2.5, and in this set of data, we'll get perfect discrimination between these two classes. So again, this is what our original plot was here in the second column, second column, first row. And that's a much less clean split than what we have with petal length. So that's an important thing about about exploratory data analysis to remember, is that even when you think that you may have gotten the pattern you want, just keep looking, keep being thorough, and whenever you cannot think of any more plots to do, that's the right time to stop. So now we're going to do one more plot, and this time we're going to show them as a heat map, because sometimes they show some patterns that aren't necessarily as obvious. So for instance, sepal width, according to this heat map, does quite a poor job at discriminating between any of the classes. And that doesn't mean that the correlation between sepal width and another feature may, but sepal width on its own seems to not do a great job. And if we scroll back up to these properties, to right up here, we notice in the first column, first row, that appears to be quite true. There seems to be a fair bit of overlap, and though green is more to the right and blue is more to the left, there's no clear separation. And then we do see, however, that things like petal length does quite a good job. And this wasn't necessarily as obvious from our scatter plots. Again, if we go to petal length, we do see that the orange and green are not as overlapping as they are in some others, but it isn't clear how much green is just sitting on top of orange as we go up this line. So what we see here is that there's actually quite good separation, and again, potentially using petal length in conjunction with, say, petal width or another feature, we might be able to separate versicolor and virginica as well. So I'm going to stop there with analyzing iris and leave it to you to do the rest, and I hope that you'll add a couple plots and just practice and think about what else you can do. I highly recommend you to go to the Plotly Python or whatever language you're using, but Plotly reference guide, and see what examples they have and just try and cater them to use our data set. And at the bottom here, I've also included links for some connectomes, fibers, tensors, aligned images, as well as some covariates that I've processed and made publicly available at the website m2g.io, as well as some notebooks and figures that do exploratory data analysis on some of these connectomes across different cohorts and populations of data. So I think that's it for now, but please play and send me a message on Slack and let me know if there's anything I can do to help.